Okay, so this one, yeah. Uh, so on a Wednesday we talk about heat conduction with some electrical sources, with electrical source, and in this case we have a wire, we have an electrical wire, and then there's a current flow inside, not flow, yeah, just the current inside uh, the wire, and because of that, because of the electricity, because of the current electricity, the electricity current, then there would be electrical dissipation, or the energy generation per volume. Okay, and then because of that there's energy generation in here, so the energy that generated here should be transferred, and then it's transferred in the form of heat. Okay, so because it's inside the solid, so the heat would be transferred inside, looks like conduction. Okay, I think it's similar with the one that you know in heat transfer, ya, operasi perpindahan panas. But in that course, you know the formula already, and then just apply it to the formula, and then you got the result. Okay, but in here we actually develop the equation by checking also all the energy balance. Okay, and here from where is it? Okay, so here similar to um, our case in circular pipe for the momentum transfer, we can find the first one. We can find the maximum temperature increase, which is on the center of the wire, or when R equal to 0, this one. Okay, and then the quantity that we often look at is actually temperature difference. Okay, so here we can see the difference between momentum balance and also the energy balance. Yeah, if in momentum balance we talk about velocity, in energy balance we talk about temperature difference. Okay, in momentum balance we talk about tau, for example, or tau yx. In energy balance, or maybe tau or z, yeah. Yeah, tau or z. In energy balance we talk about the q. Okay, and in momentum balance we talk about the force, okay, on the area, and here we talk about a capital Q, or the heat flow. Okay, now so today what we're gonna learn is actually another source of heat. Okay, let's see if we have another source of heat with this particular problems. Okay, it's called the heat conduction with viscous dissipation. So the first one, heat conduction from a heated wire, or because of the electrical dissipation. But in here is actually the heat conduction with viscous dissipation. Okay, just imagine we have two cylinder, which is coaxial. Okay, coaxial cylinder. The inside cylinder is stationary, liam, and the outer cylinders is actually rotated with some angular velocity of omega. Okay, here. Okay, so here because of that is actually we're gonna see that because it is very small, it's because the difference is very small, so we can cut the inner cylinder and the outer cylinder like this, and then we can assume that it looks like this one. Yeah, we can assume that it looks like two parallel plate. Okay, why? Because the difference of the dose diameter is very small. Okay, it's not like you have 10 centimeters and then you have 1 meter. No, maybe just like you have the inner cylinder is 1 meter and then the outer cylinders maybe 1.01 meter. So it's very small, the difference between the inside diameter and the outside diameter. So you can actually think that it is two parallel plates. Okay. Okay, so here we go. This is so here we can actually describe or guess that the inner stationary or the inner cylinder is stationary, diam, while the outer cylinder is actually have velocity of v. Okay, so then this would be the profile. We will have velocity, some velocity on the outer cylinder. So this is the outer cylinder, and this one is at the inner cylinder. Okay, so if you look at this profile, the momentum from the momentum balance, we see that Vz is actually the position of x divided by b, where b is the delta between this one, yeah, between the two parallel plates, x over b multiplied with v. So dv would be v d. So we can see that dv z equal to v over b dx. So dv z over dx is actually v over b. Okay, so because of there is a gradient velocity like this within the position of C, then we will introduce some equation which is called SV, or this one is called viscous dissipation. So viscous dissipation. Okay, so viscous dissipation, that is actually the energy that is actually generated because if we have some gradient of velocity. Okay, so that is the viscous dissipation. So if we have a difference in velocity, then some of those difference is actually will generate energy, and the energy is actually of the per volume would be the gradient of the Vz dx, which is Vb square multiplied with the viscosity. Okay, so here we can we can make it bigger. Where is it? Oops. Wait. Okay, so a viscous heating, for the viscous heating term, SV or mu Vb over b square, which is this one, may be understood by the following arguments. For the system in this system, the rate at which work is done is the force acting on the upper plates multiplied with the velocity which it moves, or minus tau xz wl multiplied with Vb. The rate energy addition per unit volume is then obtained by this quantity divided by WLB, which is given this one divided by B, or that one. Okay, so anyway, this one is actually, we call it a viscous dissipation, and this energy generation is actually would appear as heat, and then it is called as V. Okay, so let's say that we learned that this is called viscous dissipation. Right. So then what you gonna see here, that the generation of energy because of the velocity difference is called mu dv over dx square. Okay, So now again, maybe I can add one more slide here. Yeah, okay. So then let's make the energy balance. Okay, so I think I can copy again from here. Maybe I can make it this one a little bit bigger now. Energy balance of two plates on yeah, of the two plates, yeah, this one, like this. So I think I can copy two like this one. Okay, so I can copy new one. Okay, so here, so let's see the system first. So first, between those two cylinder, the smaller and the bigger cylinder doesn't have too much difference, so we can assume that it looks like a two plates. So because of it is a two plates, so then we can actually make assumption that we can use the Cartesian coordinate. Okay, now and then let's look at this one. This is the fluid, yeah. So if there's any rate of energy convective transport, if the fluid is flowing, what do you think? Do we have a fluid flowing around between these two plates? They have the velocity because of they are flowing. If something's flowing, you can actually imagine it's like if you're pouring something because of gravity, or if you look at the river, it's flowing, it has velocity. But in here, the velocity is actually caused by the plate that is moving. Okay, so then here we can actually delete that one. Okay, so there's no convective transport. If the fluid in is just like flowing by themselves, kayak apa ya? Yeah, like they have flowing or something, and then there is a pump or something, and then they can flowing. It is you can have a convective transport, but in here, the fluid is actually moving because of this solid plate is moving. Okay. Here, and then the rate of energy molecular transport, so that would be the Q when X. Okay, so that is the direction of maybe if you want to say that one, if you want to say that is the direction at X, multiply with the cross-sectional area. So we can consider the cross-sectional area is W multiplied with L, or the width multiplied with the length of the plates. Okay, just imagine that one. Okay, and then the rate of molecular energy out transfer, so it's going out that one. Yeah, so this is the Q X plus delta X multiplied with W. Okay, and the work done is not happen there. We can delete that one. This one also we can delete, and plus the rate of energy production, because we have the energy production because of the viscous dissipation, which is SV, and those SV should be multiplied with the volume of the thin shell. Okay, so this is the thin shell. Okay, this one, and then so the volume would be WL multiplied with delta X. Yeah, so that would be W L multiplied with delta x. Okay, so with that one we can write like this similar one. Okay, so maybe WL QX at x minus WL QX at x plus delta x minus WL delta x multiply with mu V over B square equal to 0. Okay, and then we can delete them and then rearrange become this one. Okay, so that now we end up with, so here we end up with or maybe just try to rearrange, maybe make them equal to this is minus, yeah, so sorry, this should be plus, yeah, this should be plus. So I'm gonna put this size to that one, so then I can get qx divided by at x plus delta x minus qx at x, okay, divide by delta x equal to divide all of them, mu phi over b square. Okay, and after that you can put the limit when when delta x equal to 0. Okay, so then you end up with dqx over dx equal to mu phi over b square, and then you do the integration to get one this one is the constant. Okay, you do the integration, so this would be the equation for heat flux. Okay, but we still don't, if you want to find the C1, that's fine, but usually we want to find the another one, the next steps, which is we can include this one is the Fourier's law. Yeah, remember the Fourier's law, which is qx equal to minus k dt over dx. Okay, so put it here, and then you have the t over dx equal to this one, and then with c1 over k, and then we do the integration, and then you get this t equal to all the value x squared minus x plus c. Okay, so here is actually now we have two constants, and then so that means we need to have a boundary condition. Okay, so we can make a boundary condition. For example, when if we say that the boundary condition, if this is from, if this one has a temperature of for example x0, t equal to t0, for example x equal to b, t would be equal to tb. Okay, just for the boundary condition. So with those boundary condition, we can have at the boundary condition 1 when x equal to x0, t equal to t0, and when x equal to b, with temperature equal to tb. Okay, so here we can so from the let's see, maybe from here, what can we do is actually we substitute them into here, so you can get the t minus 0. Yeah, so so it's basically, if we can write wait, if we can write this one there, maybe put it like that. We just crop this one. Oops. Okay. Yeah. So if you have this integration, we also know that the when x equal to x0, t equal to t0, when x equal to xb, when x equal to b, t equal to tb. And what you need to do, you can substitute into these equations. Okay, so let's say, for example, t0 equal to minus mu over k of phi over b square multiply with half equal to, let's say, 0, yeah, x is equal to 0, minus c1 over k equal 0 plus c2, yeah, so this one also 0, let's say, this is actual 0, so then t0 equal to c2. Okay, and then after that you can add when x equal to tb, so tb equal to let's say minus mu over k phi over b square half x, b, yeah, should be this one also b square minus c1 over k b plus t0, yeah, which is this one. And then try to rearrange this equation. Maybe you want to end up with this one, yeah, you can so you can get, for example, tb minus t0, yeah, which is the delta, would be equal to yeah, all that one. And then so you end up with this equation, so you end up also with tb minus t0, which is this one, yeah, minus mu k phi over b square multiply with half b square minus c1 kb. So you can, so this one is known, this one is known, this we know this one already, we know this one already, we know this one already, and then we can find the c1. So you can find your c1 and then put it back again to the equation, and then you will end up with something like this, yeah, like this. Maybe put with the equation t, this is the equation, and put it back the c1 and the c2, and then divide by tb minus t0, that one there. You end up with this equation. Okay, so that's why in the energy transfer, usually we put the difference between t minus t0 or tb minus t0. Okay, and this one is called the Brinkman number, or the Brinkman number is actually a dimensionless number, which shows you the what happened, the unit between the viscous heating and also the heat flow because of the difference in temperature. Okay, and it said that if the Brinkman number is 2, that would be a maximum temperature between the two walls, antara kedua dinding. Okay, so this is actually the temperature profiles, and then one that you can see from the viscous dissipation case, which is in this case the viscous dissipation will generate energy, and the energy will be distributed as a heat, and then it will affect the heat. Okay, so in this case also you can see, let's say when so it's gonna start when x equal to 0 up to x equal to b, so you can see where's the maximum one or the minimum one. Okay, so the viscous heating, yeah, so here maybe I can read it here. So the viscous heating SV mu over multiply with phi b over b square, it may be understood by the following arguments. Yeah, what is this one? And then in most flow problem, viscous heating is not important. So but however, if the viscous heating would be very important if you have a large velocity gradient. between like the two plates. Okay, so for example, a flow of lubricant between two rapidly moving parts. Okay, if you have a there is a two rotated part and then you have a lubricant between that, then that is flowing, then it will significantly affect the lubricant, and the lubricant is going to be heated up. Okay, and then that's why we have to change lubricant for after some time, for example. Okay, or for example, the flow of molten polymers through dies in a heat high speed extrusion. You have you know extrusion, yeah. The extrusion is the let's say the extrusion. Let me check if I have some video about extrusion. So which one? Let's see from here maybe. Maybe from which? Let me wait a while. Okay, gonna stop share and check it out. Yeah. Okay, so this is the one that I saw in the materials laboratory. What is one?
Warning ini ya. Iya. Itu kan PE kan dipakai buat lebih.
Okay, so this one, sorry, for example, you have this is how to make extrusion from polymer. Okay, so this is the polymer or the BG plastic, yeah, BG plastic. Okay, this one polymer, we put it here and it is heated up, so the polymer become fluid, become liquid, and after that we draw them, ditarik, yeah, we draw them to that one. So around here we can see that the pipe is of course stationary, yeah, diam, but inside here the polymer is moving. Okay, so because there is a gradient of velocity between the velocity of the polymer near the wall and also the polymer in the middle, which is would be very fast maybe, then that would be a viscous heating. So let's start again. They will start. It's what this one, yeah. So ditarik. Okay, so like that. Okay, or maybe, yeah, I think that would be that one. Okay, so that is one about extrusion. This is very common for making plastics or what's called the fibers and so on. And then but however, if it is a polymer, then you're gonna end up with non-Newtonian liquid, so it would be a different kind of formula for the non-Newtonian fluid. Or maybe the flow of air in the boundary layer near the Earth satellite or rockets during re-entry of the Earth atmosphere. Okay, the first two of these further complicated because many lubricants and molten plastic are non-Newtonians. Okay, so and then later on the viscous heating for non-Newtonian fluid is illustrated in problem 10b.5. Yeah, that would be just an example if you were curious about non-Newtonian fluid. Okay, so that is the end of the chapter for the conduction. Do you have any questions about the heat conduction in viscous dissipation? right? So far we have learned there's two type of problems. The first one of conduction, and then we have the source of heat is actually from the electrical dissipation. Okay, and the second one also conduction, and the source of heat is actually from the viscous dissipation. Okay, now we're gonna see the next topics, which is about convection. So I have the old one, the PowerPoints. I also have put the PowerPoints or the hands out on the EduNext, so you can have look, you can download it and have look and make notes from that one. Maybe I can copy them. Okay, but actually before that, I think it's very good if we can learn about thermal conductivity first. So I'm gonna explain the thermal conductivity first. This slide is actually made by almarhum Professor Mubiar. Yeah, he's the one of our seniors that teach transfer phenomena, and then I took it based on his PPT, on his PowerPoints. Okay, so if you look at in the Bird's book, in chapter 8, there would be about thermal conductivity. Similar with the momentum transport, you have concept of viscosity in the first chapter. Okay, so you know that one. Okay, so you know the heat transfer, the energy here. For example, if this is the direction of y, you know that the Fourier's laws of heat conduction is actually Qy equal to minus k dt over dy. Yeah, we know this already with Anggit as well, and this would be in any direction is called the q minus k divergent of t. So that means in many direction. Okay, if it is anisotropy, where the thermal conductivity is not is function of direction, then this is called the thermal conductivity tensor. It may be changed with temperature. And then this is the one that similar to, can I write something here? Okay, yeah, no, yeah. Okay, so let's say and then there is a term, it's called the thermal diffusivity. Okay, this is very important. So the thermal diffusivity is similar to kinematic viscosity for momentum transport. So if in that one, in momentum transport, pada perpindahan gerak, the one that's very important is mu divided by rho. Okay, you measure the rho or kinematic viscosity. In heat transfer or in energy transfer, the diffusivity that is important is called a thermal diffusivity, diffusivitas panas. Okay, and this one is yes, that's very important, which is also mu meter square over second, which is actually it would be equal to the thermal conductivity divided by rho Cp. Okay, with the Prandtl with the rho and the Cp, and then you actually know that the Prandtl number is actually a measure or ratio between the momentum diffusivity, which is this one, which is the kinematic viscosity, divided by a k, divided by alpha, or the k over rho Cp. So this one is your Prandtl number. Okay, and then if you look at the how is about the thermal conductivity. There's some nomogram here, but actually in our exam, the thermal conductivity will be given, so you don't need to see through the graphic. But if you want to know, or for example later on during your final project, or yeah, you need to know how to get the thermal conductivity, you can see some example here that this is a graph of reduced temperature with the reduced thermal conductivity, that there is a correlation between the thermal conductivity and the temperature. Okay, so the reduced thermal conductivity would be a function of reduced temperature and pressure. Okay, so usually if we look at with a system with different temperature, ideally the thermal conductivity should change with temperature and also pressure. Okay, and then in for gases, the thermal conductivity has formula. Okay, it based on the mean molecular velocity, which is 8k. K is the Boltzmann constant with mu, and the m, which is the molecular weight. And then if this is very theoretical, yeah, the physics, theoretical physics. If we consider exchange in energy in the collision, then the K, we can calculate it like this. Okay, this is just additional for you to know. Okay, or if you're in a gas, we can use low density, we can use Chapman and Skog to calculate the K, or the thermal conductivity. I once use this formula when I want to measure or to model the mass transfer or the thermal transfer of, for example, at that time my research was about magnesium, so about magnesium vapor, that one. So I calculate using this Chapman and Skog equation. All right, I think that would be good. So I think the one is the same. Yes, it's similar. The electrical source is similar. The viscous like this is also similar. And yeah, so that would be this one. Okay, so now let's move on to the next chapter, or the sub chapter about convection with different PowerPoints. Wait. This is too much, so I think I need to close some of the PDF. Wait, it's done. Eh. Okay, I think I need 1 minute just to grab a glass of water, yeah. Alright, now let's see about force and free convection. So first we're gonna see another example which is called the force convection. Okay, so what is force convection? The force convection, if we look at the phenomena here, you have a hot pipe, and then from the outside you have some velocity. Okay, and then because of this velocity, some of them will grab the heat, and then later on the heat the heat would be distributed. Okay, so the velocity is actually from the external forces, for example using the fan. Okay, so by calculating the velocity profil kecepatan, what you need to do, we need to calculate the velocity profiles, and after that you can calculate the temperature profile to get the fluid constant. Okay, and then in force convection we will use Nusselt number, which is a function of Reynolds and Prandtl. Okay, like a similar one. Okay, and the second one is the free convection. Oops. So in free convection, there is no fan, and actually the because of a heated or maybe because of the heated air over here, it will cause the buoyant effect, or that means that would be a difference in velocity, because the difference of density around the air around here. So and because of different density, there would be a different velocity, and after that that would be a convection. Okay, and then here the Nusselt would be a function of Grashof number and Prandtl number. Okay, and then here we have to calculate the velocity profile and the temperature profile simultaneously. Okay, but for now we're gonna talk about force convection. Okay. So let's say we have a viscous fluid which is flowing inside this pipe. Okay, it's just flowing like that with some velocity. Okay, and then we have to also assume that all the properties is actually constant, including the rho, mu, Cp, and also the K. Yeah, from the density, the viscosity, the heat capacity, and also the thermal conductivity, it should be constant, and then it's actually laminarly flow on inside a pipe with a radius of r. Okay, and then when z equal to 0, the temperature of the fluids is actually uniform, T0. Okay, but when z equal to larger than 0, then there is flux. Okay, a constant flux with in the wall, which is a Q1. Okay, so I can't write, yeah, so I think it's good if I can just crop this and then put it a PowerPoint so I can write. So I think maybe let's make a new presentation, and then insert the folder. Okay, I think it's better if I just stop that one and then change the PowerPoint like this. Okay, right, I think this is better. Okay, yeah. Okay, so go back again. So here, yeah, so so this one is the fluid viscose when z less than 0. So let's just say this is R and this is Z, okay? And then just let's say this is when z equal to 0. This one is when z equal to 0. Okay, so before z equal to 0, the temperature of the fluid is T0, like just yeah, with some uniform, okay, which is T0. Okay, so but however, when at z equal to 0, from more than the z equal to 0, there is a the heat flux, ada flux panas, yeah, the heat flux at the wall. Yeah, in this case the Q is just drawn up. Yeah, let's say just consider that inside the pipe is actually there is another jacket and then or another fan, and then they actually enforce the Q to be transferred outside with the constant hot flux. Okay, so the constant heat flux at the wall. So you can actually write this. So at R equal to R, which is on the wall, yeah, at R equal to capital R, we have Q1. Okay, that one. Okay, and then I need to make a graph again so I can draw. So maybe give me one. Okay, so oops, there. Okay, one more. Okay, so we here is actually we can see the first one that we need to see is actually we want to know what is the profile of the fluid flow. Okay, the profile of the fluid flow would be about the velocity here. Okay, the velocity. So we can see that from for the momentum balance, we know that the velocity profile Vz equal to Vz max square root of 1 minus r divided by capital R squared. Okay. Okay, and then the next one, again, we have to make the energy balance again. So for the energy balance, I need to copy them again about the the mass energy balance. Maybe I can copy it here from the previous presentation to here. Okay, yeah. So remember about this one. Okay, about the profile of this one. Okay, so here from the system we see that there is a fluid flow. Okay, so the fluid is flowing. So because of the fluid of flowing, so is there any convection? There would be convection, which is in and out. Okay, because it is the fluid is flowing. Okay, with some velocity. And the velocity is a function of the temperature. And then after that, we also have heat it up over there, okay, which is Q over here. Okay, so that means we can see that if you look at that, so in z direction, istirahat. In z direction we have that flow, yeah. In the z direction we have convection. Okay, because we know this one the temperature is T0, but because of there's a Q drawing around that one, I think that would be a change in the temperature. Okay, so there would be some convection in the z direction. Okay, and in R direction, that would be, what do you think? If there is a Q, a heat flux on the wall, there would be some conduction going happen as well. Okay, so if we look at, if we want to make the energy balance, the first one that we have to make is actually the volume element first. Or maybe the first one, we also the coordinate, and then we also sketch the system. Okay, and the third one is the volume element. We have to see the volume element. Okay, so here, if you look at here, the volume element would be in dr and also in dz. Why? It's actually, why it should be in dr, because we know that in the r direction, if this is the r and this is the z, in the r direction we have conduction. Okay, in the z direction, there is would be conduction and also convection. Okay, like that. Okay, so here when we look at the rate or the energy balance, what you can see, you have the rate energy in because of convection, so we have this one. Okay, and then we have the rate energy of convection, we have that one as well. The energy transfer molecular in and out because of there's a conduction is also, there would be there. The work done, we don't have, maybe we don't have one, and then this one we don't have the work done of this one here. And the rate energy production, there's nothing here, there's no reaction, there's no dissipation. Yeah, the electrical dissipation or viscosity dissipation maybe is very, very small, so we can delete it. So in here, for in this case, the one that has rules or has contribution is about the energy convective and also the energy by molecular transport by the conduction. Okay, so there is would be the one that we're gonna looking at. Okay, up to here, anyone, any questions? All right, so I think we should learn about the system first. So we know, once we know the system, we can go back to the handout, in the PDF handout. So I'm gonna go back again to the PDF handout. It's just all similar. I just need some time to write them. Okay. Okay, so from here again, so from the convection, again we know the PPT, when z equal to 0, the temperature, so when z less than 0, the temperature of the fluid is less than, is equal to 0, and then when z more than 0, the heat flux would be a constant with this Q. Okay, and then when we do the energy, the volume balance, the volume element, that would be the shell that we make is actually would be a function of R and Z. Okay, so now let's write the energy thermal. That this is gonna be the energy thermal in, which is this one, would be the QR at 2 VR delta Z, which is the conduction to the R direction. Okay, so the conduction, and then QZ at Z at 2 VR delta R at the conduction to the Z direction. And this one is convection. So this one is the formula for convection with the convection to the Z direction. Okay, so it's actually the Q multiplied with the cross-sectional area. The cross-sectional area is like a ring, then would be 2 VR delta R. Okay, but here is the for the R direction, the normal area would be 2v r delta z. Okay, and then we can define the energy thermal, the inlet energy thermal, and also the outlet of energy thermal, like this one, which is q r at r plus delta r, again with multiply with this one, the 2v r delta z, and then plus the conduction to the r direction, the outlet one, which is qz at z plus delta z. Yeah, this one qz, and this one is qz plus delta z, and multiply with this should be r, yeah, 2v r delta r. There's typo in here, and then plus mu cp vz delta t, multiply with that one. Okay, so and then the thermal generation is 0 because there is no reaction, there is no heat dissipation and something. So first, and then we can divide both sides with 2v delta r delta z. Okay, if you try it by yourself, you can make the energy balance like this. This is become RQR r plus delta r minus RQR at r at divided by delta r, and RQZ at z plus delta z minus QZ at z divided by delta z. Okay, so here that would be r plus RCP Vz with this delta t divided by dz. Okay, and then we can make the limit with delta r equal to 0 and also delta z equal to 0. Okay, so here so if we divide them, this sides become, this is the convection area, the convection become rho cp vz dou t over dou z. Again, this is using partial differentiation because there are two variables here, and then this one is the I think this one is the conduction to the r direction, I think. Yeah, to the conduction to the r direction, and this one is the conduction to the z direction. Okay, so this one is now the equation that shows you the heat flux compared to the raise of the temperature. Okay, so it is function of r and also function of z. Okay, and then you have to know the heat capacity and also rho and also the velocity of the fluid, and then this one also for the so then you can get the dou t over dou z, that one there. Okay, so here q to the r and this is q to the z. Well, let's substitute. So using the Fourier law, sorry, qr is actually k dou t over dou r. So we can change this with minus k dou t dou r. Okay, and then qz is actually k minus k dou t dou z. So we can change q over here with minus k dou t dou z, yeah, so inside, and we can change Vz with the momentum balance equation, which is a Vz max minus multiply with 1 minus r over capital R square. Okay, so if we substitute all of them, then we end up with this one. This is the first one, is actually the convection. This one is the conduction to the r, and this one is conduction to the z direction. And because here is the usually is very small, so we can neglect it, diabaikan, ya, for the z. So in the end, this would be the differential partial equation of the convection. So this is the convection. Rho cp vz max 1 minus r minus capital R square plus dou t over dou z actually equal to this one, which is the conduction to the r direction. Okay, if you look at here, there are variables. We can see there's a r, and also for delta R there are here, yeah, there are two, one, two, so there should be the bound, maybe, yeah, there's two over here. There should be two boundary condition regarding the radius, and then there's also with respect to z. So then we need to have a three boundary condition. The first one, when r equal to 0, the temperature is finite, yeah, it may happen. The second one, when r equal to capital R, there is a q, okay, and the q is actually equal to the Fourier's law, or minus k dou t over dou r. In boundary condition 3, when z equal to 0, we know that t would be equal to t0. So we can have three boundary conditions. All right. And sometime, and the next one, this one can be changed into a dimensionless equation. Okay, I think we can wait up to that one. Any questions? Or I think now we have three problems already. Yeah, we have three problems already from here. Let me close that one and maybe just share the desktop then. Yeah. Yeah, so at least you actually, so in the or maybe make it like that, yeah, in the blank one. So at least now you know that in energy transfer, you have learned, the first one is the introduction. You also have learned the energy balance. And then you have learned about conduction. And then this one with the electrical dissipation. And the fourth one is again conduction, but with viscosity dissipation. And the last one we learn about force convection. Okay, so, and after that we need to learn the what's called not the force convection, but the free convection. And also dimensionless number. Okay, let's try our understanding about this one by trying to let's have a look. Let me try to find some question from the last year's exam to understand. Let's try a typical question from last year's exam, and then have a look. So let's use the time for you to start think. Okay, so from this 1 hour and more, I have done the equation. I have explained to you, but just make sure that you understand. So let me check some example. Maybe from okay, let's say so this is a typical question that would be in the exam. Okay, let's try this. Okay, everyone. Okay, let's try about the conduction problem. We have two parallel plates and then so on. Okay, sketch the problem, draw the coordinates, make a shell difference balance, and construct the energy balance in steady state, and then write the boundary condition, and then solve the equation to show average temperature in the system. Alright, so I can maybe just stop the recording.